All right, so I think I'm going to do two videos today. This is going to be the third video in a series of analysis videos on elastic collisions. This one is a special one because we have a small mass. The experiment that I'm going to look at is about a small mass colliding into a heavy mass, and so we will have a reflection, and this will determine whether or not momentum is a vector or not. Well, in fact, I have done all the calculations, and this particular experiment definitely proves that momentum is a vector and that direction matters. That when the card goes in opposite direction, you have to add the minus sign to the momentum. Okay, otherwise the momentum cannot be conserved, and that's what I'm going to show you. So we're talking about this experiment here. The same person again, same YouTube channel. So as always, he's going to weigh the cards. We got a 210.5. Oh, let me use the ball so that you can see. Yes, my mouse. So mass one was 210.5 grams, which is 0.210 kilograms. Mass one.
Number two. They got it.
All right, 310.5 grams. We can clearly see the masses. That's not a lie.
Now,
Can't possibly manipulate that. He's clearly weighing it.
be careful with this experiment. See all these different
So
types.
again, we have two photo gates, one with the red tape, one with the blue tape. You can see the results over here. There's red tape to show the data of this one, and the blue tape to show the data of this photo gate.
And what should happen, I believe, is the lighter one is going to hit this one and bounce backwards. So you're going to have to read 2 times on the red timer. So you're going to have to get the video, okay? I think. Let's see. Ready? Here we go. Reset timer. Second. All right. Here we go.
All right. So the first timing is 0.1440 for the part one. All right. Put it over here. Time one equals 0.1440 seconds. And the second timing is 0.1840. Yeah, 0.1840. And now part one will bounce back. All right, which we see over here. That's the timing of part one of the reflection. 0.90, 9092. All right, so there we go. We have our data. We have to convert this into velocity. So I pick, so we need the length of the cards. I choose 0.1 meters. So we get these velocities, 0.6944 for the incoming velocity, and then after collision, the car two goes with the velocity of 0.5434 meters per second, and part one reflects back with a velocity of 0.1099 meters per second. All right, so now we're going to use this formula to theoretically predict what the velocities will be after collision. So we need this one. So mass one minus mass two divided by mass one plus mass two times the initial velocity of part one, which is over here, which is v, which is 1 prime. And so this, when I calculate this, I have calculated everything beforehand. So that turns out to be minus, since it goes in opposite direction, minus 0.1332 meters per second. This is the theoretical prediction, and the actual experimental result is 0.1099, which is close to 0.11. So we have 0.11 versus 0.13, about 2 off, a little bit more than 2 off. It's never going to be perfect, of course. Not a single experiment can be done perfectly. And it's never going to be an ideal setting. And so now the second velocity after collision, which is 2 times mass 1 divided by mass 1 plus mass 2 times the initial velocity of part 1. And that gives us a result of 0.5611 meters per second. And that's the prediction. That's the theoretical prediction of part 2 after collision. And the actual result is 0.5434 meters per second. So we have 0.56 versus 0.54. Pretty close once again. Okay. Again, this shows and proves for the third time in a row that this equation works just fine. Again, this is the exact equation that Professor Loon has used in his lecture to predict a 2/3 outcome for the second velocity and a -1/3 outcome for the one car for the first mass car, for a 1:2 mass ratio. Okay, this is exactly the same formula. So it must be really significant, must be a real coincidence for the third time that it predicts that the predictions and the results are matching so well. Okay, so now let's check out the momenta. So the initial total momentum is the mass of part 1 times the velocity of part 1 before collision. So mass 1.2105 kilograms times its initial velocity, which is 0.6944, and that equals 0.1461 kilograms times meter per second. That's the total initial momentum before collision. So now, okay, the first car after collision bounces back. According to mainstream physics, momentum is a vector, and so when it goes in opposite direction, it's going to be negative. So let's just try it out. Mass times velocity. The result is minus 0.0231 kilograms times meters per second. Then the second card after collision, its momentum is 0.1687 kilograms times meter per second. If you don't believe this, do the calculations yourself. It's true. The calculations are true. So now we have to add these ones together. We have to do minus 0.031 plus this one plus 0.1687. So we have minus plus plus. Or you can also do the other way around. 0.1687 minus 0.0231. You have to subtract. And that equals 0.1453. So this is important now. We treat momentum as a vector. We put a minus sign for the one going in opposite direction. And that, when you add that with the second momentum, that equals 0.1453. Now look how small the difference is. This was the initial total momentum, 0.1461. And when you add the momenta after collisions together with a minus sign, when you treat it as a negative momentum, then you get this result, 0.1453. 0.1453 versus 0.1461. Really close match. Not far off. Whereas, okay, according to the opposition, mainly according to draft science, you cannot, it's nonsensical to subtract momentums. You have to always add them. What happens when we add them? Then we get a result of 0.1918. So 0.1918 versus 0.1461. By the way, yeah, I wrote DSP, which means draft science momentum. So 0.1918 versus 0.1461, or when we use mainstream physics and we treat momentum as a vector with a minus sign, then we get 0.1453 versus 0.1461. I think it's pretty clear who is more closer to the initial total momentum. Pretty obvious. Again, I consider this as good proof, very good proof that momentum is a vector and that direction does matter. Okay, so now for the kinetic energy, the initial total amount of kinetic energy is 0.05075 joules. After collision, a mass 1 has kinetic energy of 0.00127 joules, and car 2 after collision equals 0.04585 joules. Now, kinetic energy, to check whether kinetic energy is conserved or not, we have to always add them together, since kinetic energy is a scalar. Always add them together. So when you add them together, we get 0.04712. So now we have 0.047 versus the initial kinetic energy, which is 0.050. Again, it's less than the initial amount of kinetic energy. 0.47 versus 0.050. Small difference, but it's normal since there's always going to be a loss of kinetic energy. So the loss, I've subtracted these both. The amount of loss of kinetic energy is 0.00363. So really a small number. So anyway, pretty conserved, pretty much conserved. Momentum is conserved. It's clearly conserved when we treat momentum as a vector. And otherwise, when we add them together, according to the opposition, we get extra momentum. So also, again, what would your prediction be in an ideal situation with absolutely no friction, when the materials of the cards are made out of exactly the same substance, when the spring constant is always the same? What is your prediction going to be for a 210 grams colliding into a 310 grams with a certain velocity? What will happen after collision? If you have a theory, then you must have a prediction. You must be able to make a prediction. Okay? Conventional physics has an equation, and it works just fine, as I have been proving for the third time in a row. And I will be doing it many more times. I've got plenty of more experiment videos to analyze. Okay, that's it for now. Not really looking forward to the response, actually.